Okay, welcome to this new part or this new topic in our course, which is thermodynamic processes and work. And so here are the main headlines that we are going to be dealing with. So in the beginning, I want to introduce a template system that we are going to be coming back often in thermodynamics because if you like, it's the simplest thermodynamic system that you can think of, and it's actually quite intuitive and useful to go back to it over and over again to understand the new concepts. So we are essentially all the time going to be talking about an expansive system or hydrostatic system, just a gas. It could also be a liquid in a container with one movable wall. That's all. Okay, so we are going to enumerate the variables of state that we need to describe the equilibrium states of such physical system, and we are going to see that they are linked by an equation of state. And linking with this observation that we made in the chapter about temperature, that when any gas is very rarefied, very low density, very low pressure, and sufficiently high temperature to be away from condensation, then all the gases seem to behave exactly in the same way. And we're going to go to that limit to see what relationship there exists in that limit between the state variables. And as you know, what we are going to get is the ideal gas equation of state. So once we have that, we are going to see how we can represent graphically the states of equilibrium of this expansive system. And we are also going to learn how you can represent thermodynamic process of between equilibrium states of the system graphically as well. So that would be quasi-static processes. We are going to learn the difference between quasi-static and reversible processes, and we are going to introduce another important type of quasi-static process, which is isothermal processes. So isothermal processes can be reversible or non-reversible, but yeah, they are quasi-static. We are also going to introduce the concept of heat source and the concept of an isobaric process as well, also important. And before wrapping up, we are going to see the equation of state, an alternative equation of state for a gas, which is the van der Waals equation. This is applicable if you are away from the ideal gas limit, and you can argue that this is more realistic for real gases. But okay, it does have limitations. We are going to go back actually to the van der Waals gas several times afterwards in the second block of the course on advanced thermodynamics. And finally, we are going to define what is reversible work, in this case expansive work, and we are going to make a little discussion of what is the work in a cyclic reversible process. Okay, so yeah, that's what we're going to do. So let's begin. And here I just remind you or connect with what we had seen in the temperature chapter. So remember that when we were defining what the absolute temperature scale was, we talked about the constant volume gas thermometer. Okay, so remember, I'm going to draw the details again, but there was something like this, and there was a capillary tube here, and okay, there was also like a larger section tube here, and so on and so forth. And this thing was filled with mercury. So the whole point is that this was filled with mercury up to there. And here, well, this has some volume, also taking into account the capillary. This is filled with gas, okay? And the whole point of this thermometer is that, okay, so there is another section of this tube here that is also filled with mercury, and the height of this mercury, this is connected with something else. The height of the level of this mercury goes up and down depending on the temperature of the gas here. So what happens, imagine that, I don't know, the temperature goes up, so the pressure goes up, and then this gas goes pushing against the mercury, and it actually moves a little bit the level of mercury down, like that, so that the gas effectively occupies a larger volume, and then your job was to put the mercury back in place by moving the the container of mercury here up and down and keep the volume constant, yes? But then this thing would move up and down. So, okay, so this is the description of the system, and what I told you is that imagine that you make markings here for the temperature to relate the height of the middle column of mercury with whatever temperature there is in the valve of your thermometer. Well, if you extract all the gas that you have here, imagine it's hydrogen, and then you fill it with something else, I don't know, some oxygen, if you make sure that the density of the gas is very low and that the pressure of the gas is very low and that you are sufficiently far away from condensation, which implies that the temperature is not too low that this say oxygen will become liquid or something. So if this is the situation, then you see that you can measure still the temperature without having to recalibrate your markings in your thermometer. It doesn't make any difference whether you have hydrogen or oxygen or anything you like there, okay? And this is telling us that there is some universal behavior of all gases when they are sufficiently rarefied, okay? And this limit is going to be called the ideal gas limit, rarefied, okay? So this also tells us that this kind of system is actually interesting to look at. Is a system essentially described by three variables of state: volume, temperature, and pressure. And the volume is changeable. It's something you can change, and that way you interact with the system. So this kind of system is what we call an expansive system, just the gas in the bulb of this gas thermometer. And normally we are going to draw to represent schematically such systems like this. So there is a container, like a box like this, and this box has certain volume and volume V. And okay, so inside of it there is a gas. Doesn't have to be rarefied, right? So it's just some gas characterized by pressure and a temperature. And we are going to make one of the walls of this box mobile. So it's like a piston that I can push or pull, and therefore I will change the volume of my system. I will interact externally with it. Okay, I'm not saying anything about the nature of the walls of this system. They could be diathermal or they could be perfectly insulating. So this is not affecting the fact that I call my system expansive system. So here, for instance, I'm drawing them to be insulating, but they could allow for heat to go through from the system to the surroundings, and yeah. So this is the thing. Okay, so this is what I would call single component. There's another important thing, which is the gas that I'm thinking is inside is a chemically pure substance. So it's a single component. It's not a mixture of gases. Okay, expansive or hydrostatic system. Okay. Also, it's worth remarking that the mass of the gas that I put inside is another relevant variable of state. In principle, if you list the variables of state to completely specify an equilibrium state of the system are pressure, temperature, volume, and mass. And remember, pressure and temperature are intensive and volume and mass are extensive. So the mass, in our case, is always going to remain constant because these walls may let heat to go through, but they don't let mass to go through. So there's no leakage of gas or there's no gas being injected. So this variable is actually constant. So it doesn't really play a role in a thermodynamic process. And we focus on these three. And the main point I wanted to remark now is that pressure, temperature, and volume are not independent from one another. We just saw it here, okay? So for instance, we said that we know from experience that when temperature goes up and the volume remains constant, well, pressure also goes up, okay? And exactly how or what is the functional relationship between temperature, pressure, and volume, we don't know, but we know it exists. And this kind of functional relationship between the thermodynamic variables that describe any physical system is called equation of state. So in a given system, when in a simple system like this, with only three thermodynamic variables, there's only one equation of state. But you could have more complicated systems, and you will learn about this in the first self-study pack, which is some simple thermodynamic systems and how you calculate reversible work on them. You will see that you can have hybrid systems, combined systems with more variables of state. And in that case, you can have more equations of state. Okay, so these equations of states are just constraints between the variables that tell you that not all of them are independent from one another. There's just a subset of them that you can consider independent. Okay, so that's it for now.